Hi everyone! Now that we have a list of new shortcuts for all of the trig functions, I'm just going to work through a set of examples to show you how I'm combining those with the shortcuts we got from 2.1. So I'm just going to jump right into A. At any point, if you feel like you've kind of got the idea and you want to pause and try the problems on your own, I think that's excellent. First example is just a really standard, we're given the function, find the derivative, nothing else to worry about here. So when I look at this function h of t, the first thing I notice is that the big operation here is addition and subtraction. That's the last thing happening, which means the first shortcut that gets applied is actually the sum and difference shortcut, but that one's a really easy one. And it almost feels like a non-rule. It basically just says you're going to look at this one piece at a time, and while you're taking the derivative of each piece, you don't have to worry about the rest. Okay, so I move on to piece number 1, 3 times cosine t. The next thing I have to think about here is the multiplication. This is multiplying by a constant, and we do have a shortcut for that. It says if you are multiplying a function by a constant, its derivative will be that constant multiplied by the derivative of the function. So basically, the constant just comes along for the ride. You just copy it down. And then finally, we get down to the function, cosine t. The derivative of cosine is minus sine. So I'm going to rearrange just a little bit here. I'm going to give myself some room. This becomes a negative 3 sine t. So 3 multiplied by negative sine t is what I end up with. Next, the minus just carries down from above, and so does the 4. Once again, that's a constant multiple of a function. So the 4 will carry down and will get multiplied by the derivative of sine t. The derivative of sine t is cosine t, and then I'm all set with that one. That's probably our cleanest shortcut for trig functions. Next, we hit the plus, which just carries down. And I have a tangent t, so no constant multiple this time, which means I get to go straight for the shortcut to tangent, which you should be trying to memorize. The derivative of tangent is secant squared t. So that is my final answer to this question. Part B asks us to go just one step further. We're supposed to find the slope of the tangent line to f of x equals 2x plus cosecant x over 2. When x is pi over 6. So to find slopes of tangent lines, you first need derivatives. So I need to find f prime of x, and then I'll just need to plug pi over 6 into that derivative. That's how we would get a slope of a tangent line. So again here, the big operation is actually the addition. So I get to look first just at a 2x, and then I get to look just at cosecant x over 2. The derivative of 2x is just 2, so you can think about that as a linear function, y equals 2x, the slope is 2. Or you could think about that as a power rule. I drop the 1 down in front, I get 2 times 1x to the 0, which is just 2. For the cosecant, remember that dividing by 2 is the same as multiplying by 1/2. So this is the same as 1/2 cosecant x. The plus just carries down, and the 1/2 also just carries down once we think about it that way. So we're really just worried about the shortcut for cosecant. And what we have is that the derivative of cosecant is negative cosecant x cotangent x. So that's my derivative. From there, I need to plug in pi over 6. So I'm going to get 2 minus 1/2 of cosecant pi over 6 times cotangent pi over 6. So this takes a little bit maybe of reviewing some of your special values, but pi over 6 is towards the bottom of quadrant 1. So that would have coordinates root 3 over 2, 1/2. Which means that sine is 1/2, so cosecant will be 2. Cosecant is the reciprocal of sine. Cotangent is maybe just a little bit messier. Cotangent is cosine, which is our x value, divided by sine, which is our y value. And then you can flip and multiply, and actually you get to cancel 2's, so all that's left is a root 3. So we have 1/2 times 2 times root 3. That 1/2 and that 2 are going to cancel, so we're just getting 2 minus the square root of 3. And that's how you should leave your answer. It said exact, which means no decimals. You want to leave it just like that. All right, next one. Find the equation of the tangent line to g of x equals x squared plus 2 cotangent x at the point where x is equal to pi over 2. Okay, so one step further than part B now. We not only need to find the derivative and then the slope for the tangent line, but we then need to put that together and make an equation for our tangent line. So g prime of x first. G is a sum first and foremost, so we'll look at the x squared on its own, and we'll look at the 2 cotangent t on its own, and we'll take the derivatives and add them up. So the derivative of x squared is 2x, and then that plus just carries down. The constant multiple 2 carries down as well. The derivative of cotangent was negative cosecant squared of x. So this is my derivative. I'm supposed to build a tangent line. So I need a point and a slope, and the slope comes from this derivative. So I need to plug pi over 2 in. So I get 2 times pi over 2 minus 2 times cosecant pi over 2 squared. And I am being deliberate with my rearranging where I'm writing that squared. That means the same thing, but people can get a little confused when I write the square on the cosecant and they're trying to evaluate. So really the order there is figure out cosecant of pi over 2 and then square it. So if I'm thinking of my unit circle, pi over 2 is at the top of the unit circle and sine is 1. So cosecant, which is the reciprocal of sine, is also 1. 1 over 1 is still 1. So in here, I really have a 1, and 1 squared is still 1. I'm saying 1 way too many times. So really, I'm just getting a pi minus 2. 2 times 1, but just 2. Okay, I also need a point if I'm going to build a tangent line, and you get the point from the original function. So if I plug pi over 2 into the original function, I get pi over 2 squared, and 2 times cotangent of pi over 2. Okay, so cotangent of pi over 2. Cotangent is cosine over sine, which is 0 over 1, so this is just 0. So my point is, well here, let me write this first. So this just equals pi squared over 4, and my point is pi over 2, pi squared over 4. So if I'm going to use point slope form, and that is what I'm going to do, I'd say y minus pi squared over 4 equals my slope, pi minus 2, times x minus pi over 2. And we should for sure solve that for y. I think I'm also going to go ahead and distribute that pi minus 2 through the parentheses. So I get a pi minus 2 times x minus pi minus 2 times pi over 2, and then adding from the other side a pi squared over 4. And really that's pretty good. We maybe want to go one last step just to clean up here, but be very careful. There's a minus sign and a pi over 2 that have to distribute. You can distribute the x through. I'm kind of inclined to leave it because then it's really clear that slope is that entire pi minus 2 part, so I leave that up to you. Pi minus 2 times x. In the second set, I get negative pi squared over 2, and then plus pi. So the rest of that is a negative pi squared over 2 plus pi plus pi squared over 4. And you could actually combine this pair as well. Pi squared over 4 minus pi squared over 2. That's a quarter of pi squared minus half of pi squared. That becomes negative 1/4 pi squared, or negative pi squared over 4. But I'm okay if you leave those two separate. Okay, so kind of a messy one, but good example here on being able to work with exact values and not converting things to decimals. All right, just a couple more parts. This one is back to just taking the derivative, so not all that messy tangent line stuff. We have p of z equals z to the 4th plus 4 to the z plus 4 secant z minus sine of pi over 2. So if I want to apply my shortcuts, the big thing there is the addition, subtraction. So I'm going to look at each piece on its own. The derivative of z to the 4th, that's a power rule. The 4 drops down and it becomes 4z cubed. 4 to the z is not a power rule. If the variable is in the exponent, it's exponential. And the exponential shortcut is you get the exact same exponential function. So 4 to the z's derivative is 4 to the z times the natural log of your base. So the natural log of 4 in this situation. And then I have 4 secant z. So the 4 is a constant multiple that just carries down. The derivative of secant is secant z tangent z. And then last I have minus sine pi over 2. A lot of people will get tricked by this one, but notice there is not a z anywhere to be found in that last chunk. Sine of pi over 2 is a constant. In fact, sine of pi over 2, if you look back up at our unit circle, is just 1. So we're taking the derivative of 1, which is 0, and we don't even need to write that at the end. So watch for those tricky constants. They catch people a lot. Okay, last thing that you'll probably run into is some applications of trig functions. They lend themselves really nicely to different applications. In this one, we're looking at an animal living on a small island, and we have a function that gives us the population in hundreds, so I want to be careful about that. T decades since 2010, so both of them have kind of funny units, so we'll want to pay attention to it. We want to figure out what the instantaneous rate of change is on January 1st, 2030. Okay, so first thing I notice is January 1st, 2010 to January 1st, 2030 is 20 years, which is 2 decades. Okay, so I'm going to be looking for what's happening after 2 decades. And instantaneous rate of change, that is derivative. So we're going to take p prime of t. And the big thing happening there is the addition. But I also want to notice that the first part of that is just a constant. So it really becomes 0 plus. And you don't have to write that part if you don't want to. You can just leave the 0 plus off. I'm then left with an 8 sine t. 8 is a constant multiple, so it will just carry down. The derivative of sine is cosine, so I really just get 8 cosine t. And I'm supposed to be plugging a 2 in, as I figured out earlier. So I'm looking for 8 cosine of 2. For something like this, make sure your calculator is in radian mode. I think it's probably safe to set your calculator in radian mode for the entirety of calculus, unless the problem specifies that you're getting degrees, not decimals. You want to be in radian mode. So when I plug this in, I get approximately negative 3.329. And then we're supposed to explain how the population is behaving. So basically we're supposed to interpret the number that we just got. So I'm going to rewrite it as a fraction because it is a slope. So we always want to think change in y over change in x. The top is the change in population. Remember that had kind of funny units. It's hundreds of animals. And then the bottom is change in time, but time was in decades. So I would say if we convert that, because it said hundreds, so that's 330, yeah, I am going to go 333. So it would be 332.9 animals, but I think that it's probably okay to round that up for the purposes of our explanation. And that's per decade. So to say it all, I would say that on January 1st, 2030, the population is increasing at a rate of 333 animals per decade. Okay, so there are a bunch of examples. So it's basically just continuing to do the same types of problems we've been doing. We're just adding new shortcuts that we can use to find the derivatives more quickly. And again, these are all 6 shortcuts for the trig functions, except I see a typo of my own right here. Cosecant should have a negative in it. There we go. Now I think it's good. So work on memorizing those, and we'll keep adding new shortcuts as we go. Thanks for watching.